Hey everyone, happy Star Wars Day. Last week we looked a little bit at properties of acids and bases, and you all did a PhET simulation to explore some of those properties. This week we're going to go a little bit more in depth into pH. So let's go ahead and get started. Okay, so from last time, we know that a solution where pH equals 7, that's going to be neutral, right? That's something like water or something else neutral. A solution with a pH less than 7 is acidic, and a solution with a pH that's more than 7 is basic. And from the PhET simulation, you might have seen that there were a whole bunch of examples of acidic solutions, right? So milk, chicken soup, coffee, orange juice, soda, vomit, battery acid were all acidic. And then drain cleaner, soap, blood, spit were all basic. Now, one of the questions asked, okay, which one is the most acidic and the most basic? So a pH of 7 is neutral. Anything less than 7 is going to be in an acid. It's going to be an acidic solution, right? The closer the pH is to 7, the closer the solution is to neutral. That is, the less acidic it is. So in order to get the most acidic, you want the pH to be the furthest away from 7. You want the pH to be as low as possible. Right, so the lowest pH, that would give you the most acidic solution, which in the simulation was battery acid. For solutions that are basic, for a solution to be basic, it needs to have a pH that's more than 7, right? The closer you are to 7, the closer the solution is to being neutral. The higher the pH, the further away you are from 7, so the higher the pH, the more basic it is. So when you're looking for something that's the most basic, you want the highest pH, right? That would be the most basic solution. So in the simulation, that was the drain cleaner. That's like Drano is super duper basic. Cool. We talked last time about the fact that acids give off H+ when they dissolve in water. So for example, an acid like HBr might dissolve in water to make H+ and Br-. Okay, well, I want to know what actually is H+. Take a minute to think about this question. What is H+ in terms of elementary particles, right? So how many protons, neutrons, and electrons are in H+? Think about that. So normal hydrogen has 1 proton, 1 electron, and a mass of 1. That's what the periodic table tells us. So if we've got 1 proton, 1 electron, and a mass of 1, well, the number of protons plus the number of neutrons has to equal the mass. And so if the mass is 1 and there's 1 proton, that means there's 0 neutrons. So normal hydrogen, elemental hydrogen, would have 1 proton, 0 neutrons, and 1 electron. H+ is positive, so that means it's lost an electron. So that means, okay, well, it started out with 1 electron. If it's lost, it has 0 electrons. So H+ has 1 proton, 0 neutrons, and 0 electrons. In other words, it's literally just a proton. So oftentimes in chemistry, you'll see H+ referred to as a proton. And you'll sometimes see the phrase, oh, acids are proton donors. That's another way of saying acids lose H+, right? That's exactly the same thing as saying acids lose H+. These are just 2 different ways of saying the exact same thing. Now, H+ is a proton, right? So that's just a proton. Well, a proton is a positive charge with no negative charge. And a proton on its own is actually really unstable. So when acids lose H+, they actually never just lose H+ on their own. So a chemist might write this equation to sort of show that HBr dissociates, but this H+ doesn't actually stay on its own. Instead, it's always going to bond to another molecule. If you're dissolving an acid into water, the nearest molecule is going to be a water molecule. So really, if you were to dissolve HBr in water, a more accurate way to write the chemical equation for what happens is that the H+ gets lost and then bonds to the water. If H+ bonds to water, you're going to form H3O+ hydronium, right? And then Br-. So When acids dissolve in water, they really form hydronium, right? Every acid forms hydronium when it's dissolved into water. Sometimes you'll see a textbook write H+, and sometimes I'll write H+, just as a shorthand, but anytime someone writes H+, right, they're really being lazy. Anyone who writes H+, aqueous, that is actually shorthand for H3O+. Right? A hydrogen by itself, H plus by itself, a proton by itself, would never float around by itself in water. It'll always get attracted to the negative charge of a nearby oxygen on a water molecule, and it'll stick to that oxygen and form H3O+. So when we write H+, we really mean H3O+. We're just being lazy and like not wanting to write the 3 and the O if we write H+. Okay, so we looked at this simulation for homework, and I wanted to just point out a couple of key details. So if you look at the H3O plus and OH minus ratio, you can see they, in the micro version, they've got these basically particles representing, these little dots representing those particles. And you can see for a solution that's neutral, we have the same concentration of H3O plus and of OH minus. And you can see that represented here, right? There's basically the same number of dots. Let's switch to something that's a little bit basic, right? So spit has a pH, it's pretty close to neutral. It's almost 7, it's 7.4, right? So it's very close to neutral, right? The pH is only 0.4 away from water. And yet, if you look at the particle diagram, you can see that there's a lot fewer H3O plus and a lot more OH minus, even though the pH hasn't changed very much, right? If we go for something that's a little bit more basic, like hand soap, which is a pH of 10, right, which isn't even the most basic substance on our list, already we've got way, way, way more OH minus and almost no H3O plus. If we go the other way to something that's a little bit acidic, like chicken soup that has a pH of 5, right, we can see that we've got almost all H3O plus and very, very little OH minus. If we look at coffee, same deal, right? It's almost all H3O plus, almost no OH minus. Even though the pH has only gone down by 2, we've gone from 7 to 5, right? So it's worth noticing that when the pH changes a little bit, the ratio of H3O plus and OH minus changes dramatically. It has these huge, huge changes. If we look at our scale over here, we can see that we're going from a neutral solution, which has 10 to the negative 7 concentration of H3O plus, to, for example, our coffee, which is pH of 5, now 10 to the negative 5, right? OH minus has gone in a neutral solution from 10 to the negative 7 to, in a solution with pH of 5, 10 to the negative 9, right? So that's changed by a factor of 100, right? This solution that has a pH of 5 is 100 times, has 100 times as much H3O plus, and 1/100 times, 1/100th as much OH minus, right? And so these concentrations are varying really, really wildly. They're fluctuating wildly as we change the pH, right? So ordinary solutions have H3O plus concentrations that vary really, really dramatically. And so it would be, we could talk about how acidic something was by talking about the concentration of H3O plus, but that starts to get a little bit confusing because we're looking at numbers that are ranging from essentially around 1, right, up to like, or down to something like 10 to the negative 14. Okay? And as we go from a solution that's neutral to a solution that's mildly acidic, like coffee, the concentration is getting multiplied times 100, right? If we went to something a little more acidic, like orange juice, the concentration is now getting multiplied times almost 1,000, right? If we went to something like battery acid, right, the concentration is getting multiplied times 1,000,000. And so we're getting these really, really dramatic changes in concentration, it's hard to talk about those numbers using the actual numbers. It actually gets a little bit confusing. And so we basically are dealing with exponential changes, right? The concentrations are changing exponentially as we're going from a solution that's neutral to something that's a little bit acidic to a little more acidic to quite acidic to very, very acidic, right? The concentration of H3O plus is changing exponentially. And we see that in our simulation here, where our neutral solution has a lot of both of these particles, but even a solution that's just a little bit acidic, right, 6.5, already we're seeing this huge difference in the number of H3O plus particles versus the number of OH minus particles. And so the best way to deal with that is by using a logarithmic scale. Cool. In the PhET simulation, you saw that in a neutral solution, the amount of H3O plus equals the amount of OH minus. And you also will sometimes see square brackets. Square brackets are used to represent concentration. So if I don't put the square brackets, I'm saying like the number of H3O pluses equals the number of OH minuses. If I put the square brackets, I'm saying the concentrations are equal. If we're talking about one solution, if the concentrations are equal, the number of particles will be equal. And if the number of particles are equal, the concentration will be equal. So in this case, it doesn't really matter too much. But these square brackets represent concentration. Cool. So in a neutral solution, these are going to be equal. In a solution that's acidic, you saw in the PhET simulation, the acidic solution now is going to have more H3O plus, and it's going to have less OH minus. And so now the concentration of H3O plus is going to be larger than the concentration of OH minus. And for a basic solution, the opposite happens, right? A basic solution, bases give off OH minus, and so in a basic solution, you're going to have more OH minus compared to the amount of H3O plus. We can measure how acidic a solution is by measuring the amount of H3O plus, or, if we're being lazy, H plus. Right? And we saw in the video that that amount fluctuates really dramatically. It can range from about a concentration of maybe 1 down to a concentration of 10 to the negative 14. Right? And so because that amount ranges so dramatically, it's helpful to use what's called a log scale to measure how acidic something is. So pH is based on a log scale. The actual mathematical equation for pH is negative log of the concentration of H plus. And recall that when we write H plus, we're being lazy, right? When we write H plus, we actually mean H3O plus. So we could equivalently write negative log of the concentration of H3O plus, right? We could do that either way. Okay, well, in order to understand what that actually is, we need to know a little bit about what a logarithm actually is, right? So let's go ahead and look at some example problems, and then we'll talk a little bit more about using logarithms and using this equation. So I've pulled up 3 example problems. Take a minute to actually answer these example problems on your own. All right, so for the first one, we've got 2 to the power of x equals 16. So 2 to what power equals 16? Okay, well, 2 squared is 4. If we multiply that by 2 again, that's 8. If we multiply that by 2 again, that's 16, right? So we've multiplied 2 times 2 times 2 times 2, so 2 to the 4th, right? 2 to the 4th is 16, so x in this equation must be 4. If we look at problem number 2, 3 to the x equals 27. Okay, well, 3 squared would be 9, and then times 3 again is 27. So 3 to the 3rd is 27. So x in this equation is 3. Okay, and then 5 to what power is 1? Okay, well, anything to the 0th power is 1. So in this problem, x must be 0, right? Because anything, if you take it to the 0th power, you're going to get 1, right? Now these equations are pretty straightforward, but what if we had an equation, for example, that looked something like 3 to the x equals 20. Okay, well, 3 squared, I know that 3 squared is 9, and 3 to the third is 27, and we're looking for something that's in between. So x is definitely somewhere in between 2 and 3. But it's not obvious what exactly x is, other than that it's somewhere in between 2 and 3. Right? In order to be able to solve this equation for x and get an exact value, for which there is an exact value, it's a decimal, it's not a whole number, but there is an exact value of x, we need to basically reverse this exponent, the exponent that's in this equation. The inverse function for an exponent is what's called a logarithm. So the relationship between logarithms and exponents is kind of the same as the relationship between multiplication and division, right? Multiplication and division are inverses. Division is it basically reverses multiplication. Taking a logarithm reverses an exponent. The exact definition for logs is if log base b of x equals y, then x equals b to the power of y. Right, this is our definition for logarithms. If log base b of x equals y, then x equals b to the y. So we could actually go up and rewrite each of these equations to have a log. Right, so this equation says 16 equals 2 to the whatever. So instead, we could write that as, let's see, okay, so the 2 is basically in the place of b. So we would write log base 2, right? I'm putting the 2 where the b is here, right? Because the 2 is the b. Log base 2 of, in this equation, 16 would equal x. So log base 2 of 16 equals x, which is, we said 4. Log base 2 equals 4. So 2 to the 4th power equals 16. Log base 2 of 16 equals 4. And we can do the same for our other equations as well. So for equation number 2, we would do log base 3 of 27 equals x, right? And in this case, x was 3. For the last one, we would do log base, right? And the base is the thing that's being raised to the power, right? So log base 5 of 1 equals x, which was 0. So log base 5 of 1 equals 0. So anytime that you are using a logarithm, right, you're basically reversing an exponent, right? So log base 5, and you put as your base whatever you want to take the exponent of, log base 5, and then this is, okay, this is the number that you get from this base, right? So this base raised to this power gives you this number. So 5 to the 0th power gives you 1, right? B to the y power gives you x based on this definition. So the base to the other side of the equation power gives you this number. So we could rewrite this equation as using a logarithm, right? So take a minute to do that. Okay, so we're gonna write log, and then we want our base to be whatever's being raised to the power. So in this case, I would write log base 3, right? And then the other side of the equation is what goes here. So log base 3 of 20 would equal x. And now I have an equation that I can actually solve for x. I could go ahead and plug this directly into my calculator to get a numerical value for what x is. Cool. You'll sometimes see equations written without a base written in, right? So you might see something like log 20 with no base written in. If there's no base, then the default assumption is that the base is 10, right? Because we so often, since our number scale is based on tens, we very often will be dealing with exponents where it's 10 to some exponent, right? Anytime you have scientific notation, you have 10 to some exponent. So if there's no base written, then the assumption is that it's a base 10. No base written, then you assume that's base 10. So log 20 would be the same thing as writing log base 10 of 20, right? 10 to what power gives you 20. Knowing that, let's go ahead and look at a couple more practice problems. So go ahead and take a minute and see if you can find the answer to these 3 practice problems. All right, let's do this. So none of these have a base written in. So that means they're all base 10. So we have 10 to what power gives us a million? Well, a million is really, we could rewrite this, right? This is really 10 to the 6th. So 10 to what power gives us 10 to the 6th? Well, we know that 10 to the 6th power gives us 10 to the 6th. So the answer here is 6, right? Problem 2 is saying 10 to what power gives us 0.1. Well, if you remember 0.1, 0.1 is actually the same thing as 1/10. So 10 to what power gives us 1/10, right? 1/10 is the same thing as 10 to the -1. So 10 to what power gives us this number? It's -1, right? 10 to the -1 gives us 1/10 or gives us 0.1, right? And then here, log base 10 of x equals 3, x equals what? So this equation, in order to solve it, we need to reverse the log. We need to take the exponent of both sides. So this equation, we can reverse the log by saying, okay, this is telling us 10 to the 3rd power equals x. So in other words, x equals 10 to the 3rd, that's 1,000. So in this problem, x is 1,000. Hey folks, tonight's homework is going to be some general practice using logarithms, but then we're going to look a little bit more at pH specifically on Wednesday. But before we go, I wanted to just talk to you a little bit about using a log scale in general and why we would use it. Log scales are really useful when you're dealing with measurements that range really dramatically. So if you were dealing with measurements like a child's height as they're growing over the course of their life, right, you wouldn't need to use a log scale because essentially they're increasing in small amounts and kind of roughly the same amount over time, right? But if we wanted to, for example, look at the size of the universe, it might help us to use a log scale. So I pulled up one of my favorite cartoons. This is XKCD, and this particular strip is the observable universe, but measured on or drawn on a log scale, right? And so what a log scale lets you do is it lets you see both large and small things with a pretty good amount of detail. So we can see roughly on the log scale the height of humans and the pyramids and the Eiffel Tower and Mount Everest, and all of this, because we're on a log scale, is getting kind of compressed together, right? If we were measuring on a real, actual linear scale, Mount Everest is a lot taller than the Eiffel Tower. It looks here like Mount Everest is about twice as tall as the Eiffel Tower, which isn't true, right? This is because this is being measured on a log scale. But now we can see, okay, here's the edge of space. Here's where most of our satellites are and the moon. Up here is a lot of the planets and the sun, right? Here we've got the shell of radio transmissions that we've been sending out from Earth and the edge of our galaxy, some of the other galaxies, right? All the way up to the top of the observable universe. And so if we were trying to graph this on a linear scale, there's no way that you would be able to draw a picture where you could see the Eiffel Tower and you could also see, oh, here's how big the universe is, right? If you drew the Eiffel Tower this big, well, the universe would be, you know, you would need a piece of paper bigger than the size of the Earth to handle how big the universe is, right? if you wanted the universe to fit on a piece of paper, then the Eiffel Tower would be microscopic if you were using a linear scale. And so using a log scale lets us basically deal with these really, really huge fluctuations. And we use a log scale for pH for exactly that reason. pH, or concentration of H3O plus, hydronium, fluctuates wildly, right? It ranges from essentially 10 to the negative 14 up to a concentration of about 1, right? And so in order to account for these wildly dramatic fluctuations, where it could be, one solution could have 1 trillion times as much hydronium as another solution, and that's not even a big difference. That's the difference of 10 to the, it's a difference of a pH of 9. It's a big difference, but it's not the biggest difference you could have even with ordinary solutions that you could find at home. And so in order to handle those wildly dramatic changes, we use a log scale. Okay, stay safe and may the 4th be with you.